Today I make the video on mechanism of organic reaction. Introduction. During a chemical reaction, the reagent are converted into the product molecule. The arrangement of the atom in the product molecule is altogether different from the present in the reactant molecule. This change, which is brought about a redistribution of electron, usually occur through the different defined step. A detailed step by step description of the chemical reaction solved as a how the reactant are converted into the product is called the reaction mechanism. In this unit, we shall be study about the important aspect of the organic reaction mechanism. First topic, arrow notation in the organic reaction. Organic reaction usually involve making and breaking of covalent bond. A covalent bond is often represented by a dash, and the movement of pair of electron is shown by a curved arrow. The movement of single electron, on the other hand, is shown by a fish look arrow or half arrow. For example, you have seen in this notation the tail of the arrow indicate the side where the electron or a single electron is have to be moved, and a head indicate the side to which it has been moved. In contrast, the double bond arrow do not indicate the movement of electron, but it is used to separate the console structure. For example, benzene be reread as a resonance hybridide of two kequl first and second and three diquel structures as shown. Type of bond fusion. Organic reaction occur by making or breaking of bond. There are two ways in which the covalent bond can be broken, and these two are homolytic or heterolytic. Homolytic fusion. When a covalent bond join A and B and break in such a way that each of the covalent bond take always one electron of the shared pair, and this is called symmetrical cleavage or homofusion or simply homolysis. The natural chemical reaction which contain an odd or unpaired electron and which are produced by homolytic fusion or covalent bond are called free radical. The homolytic fusion usually occur in non-polar bond and is favored the high temperature gases or pyrolysis or under the influence of ultraviolet radiation by the presence of radical indicators such as peroxide. Heterolytic fusion. When a covalent bond join together A and B, breaking in such a way that both the electrons of the covalent bond are always by one of the bond atom, the mode of bond breaking is called unsymmetric cleavage or heterolytic fusion. Simply heterolysis. Heterolytic fusion is usually indicated by a curved arrow with a denote of two electron displacement. For example, see. As shown above, the heterolytic fusion result in the formation of ionic species, cation and anion. Further, the heterolytic fusion usually occur in polar bond and is favored by a polar solvent. Quite often, the ionic species formed by the heterolytic fusion occur by positive or negative charge on the carbon atom. Such ionic species is called the carbocation or carboanion respectively. According to the carbon carry positive negative charge, it may be implied here that the same covalent bond undergo the homolytic or heterolytic fusion under different conditions. In general, the bond dissociation energy for the homolytic fusion are low while are quite higher for heterolytic fusion. For example, homolytic fusion give rise to free radical and heterolytic to the anions, reagent and the substrates. We know that whenever an organic reaction is carried out, we use a certain starting material called reagent and therefore which are classified as reagent and substrate. Actually, there is no clear cut distribution between these two because each of them cannot be react in absence of other. In general, one reactive agent is called reagent, while the another less reactive agent is called substrate. A substrate is more preserved, is defined as a reagent which contain carbon atom of those bond which with the other atom are broken and new one is formed as a result of reaction with the reagent. For example, ethylene plus we are going to ethylene bromide. Ethylene is substrate and bromine is reagent. Type of reagent. Reagents are broadly classified into two types: neurophasic reagent and electrophasic reagent. Neurophasic reagent. These reagents or are electro-loving chemical species which therefore loss of the electron is due to presence of electron deficient atom in them. The electrophile are of two types: positive electrophile, the electrophile in which the electron deficient atom carry a positive charge are called positive electrophile. Example: proton, hydronium ion, bromine ion, chlorine ion, carbonium ion, nitronium ion, etc. Second is neutral electrolyte. The electrolyte in which the electron deficient atom does not carry any charge are called neutral. For example, free radical, carbenes, nitrines, bromines, trifluoride, aluminum chloride, ferric chloride, strontium chloride, etc. In the Fe3, aluminium 3 and FeCl3 etc. These central atoms have the 6 electron in the valence shell and tugs. The strong tendency is acquired a pair of electron to complete its octet. However, in the case of SnCl4, the center atom has required octet of electron in a valence shell but still strong desire to accept more electron because of the presence of vacant d orbital in it. Since both the positive charge and the neutral electrophile are short by the pair of electrons, they have a strong tendency to skip the electron from the source and Turks believe as Lewis acid. Due to attractive interaction of for the electrophile always attack to the substrate the molecule at the site of higher electron density. Nucleophile reagent. The nucleophile reagent or the nucleophiles are the nucleus loving chemical species. Since the nucleus of the atom is positive charge, therefore the nucleophile must be electron rich chemical species containing at least one unshared or lone pair of electron. There are two types: negative nucleophile. These nucleophile which contain the unshared pair of electron and are also called the negatively charged are called negative nucleophile. For example, halidine, hydroxidine, alkaloxide, amidine, cyanidine, carbamine, acetylide, etc. Neutral electrophile. The electrophile which contain unshared electron but don't carry any charge is called neutral electrophile, like water, ammonia, amine, alcohol, trioalcohol, hydroamine, Grignard reagent, alkyl, lithium aluminum hydride, sodium hydride, etc. Since both the neutral and negative charge electrophile contain at least one lone pair and they have a strong tendency to donate this pair of electron to the deficient atom or the species, hence they are believed as Lewis base. In another word, the nucleophile always attack the substrate molecule at the site at least electron density. Type of organic reaction. There are the 7 type of organic reactions. First is substitution, second addition, third elimination, fourth condensation, fifth rearrangement reaction, and sixth is isomerism, and seventh is paracyclic reaction. First, substitution reaction. in the substitution reaction is that which involve direct replacement of atom or a group of atom in an organic molecule by the another atom or a group of atoms without any change in remaining part of the molecule. The incoming group get attached to the same carbon at which the outgoing atom group was attached. The product obtained as a result of substitute is called substitution product, and the new atom or group of the atom which entered the molecule is called substituent. Depend on the nature of attack, nucleophile, electrophile or a free radical substitution reaction are followed by the three type. First है हमारी nucleophile substitute reaction. The substitute reaction which are brought about a nucleophile are called nucleophilic substitution reaction. In all these reaction, a strong nucleophile usually display a weak nucleophile. Therefore, the reaction are typically of alkyl halide. For example, hydrolysis of alkyl halide with aqueous base to an alcohol. Second is electrophilic substitution reaction. The substitution reaction which are brought about the electrophile are called electrophile substitution reaction. In this reaction, the attacking species is the electrophile and the leaving group with the pair of bond electron. These are the typical of arenes and other aromatic compound which have the higher density to of the aromatic ring to attract the electrophile. For example, halogenation, nitrogenation, sulfonation or free radical Kraft reaction. The another third is free radical substitution reaction. The substitution reaction brought about a free radical are called free radical substitution reaction. These are typically of the alkane and other unsaturated compound. For example, chlorination of methane in the presence of heat or diffuse sunlight to give the methyl carbide and hydrogen chloride. The reaction occurs by the free radical mechanism involved the following three steps. First, initiation in which the chlorine bond will be break and give the chloro-free radicals. Second, propagation in which the methane group plus free radical carbene free radical give rise to free radical of methyl. And second, the termination in which chloride and ethane is formed. Second, addition reaction. The reaction which involve combination between two reagent molecule to give a single molecule of product are called the addition reaction. Such reaction are typically of compound containing multiple double or triple bond depend upon the nature of attaching species, electrophile and nucleophile or free radical. Addition reaction of the following three type. The nucleophile addition reaction. A addition reaction brought about a nucleophile are called nucleophile addition reaction. In the reaction are called typically of aldehyde ketone. For example, base catalyst adding of HCN to aldehyde or ketone. Second is electrophilic addition reaction. The addition reaction brought about the electrophile are called electrophilic addition reaction. These reactions are typically in alkenes and alkyne. For example, addition of Br2 or HBr to the propylene. Third, free radical reaction, addition reaction. Addition reaction brought about the free radical are called free radical addition reaction. For example, addition of HBr to alkene in the presence of peroxide. This is also of three type: initiation, propagation and termination. Third type of reaction is elimination reaction. Elimination reaction is one that involve loss of two atom or group of atom from the same or adjacent atom of the substance lead to the formation of multiple double or triple bond depend upon the relative position of the atom or group eliminate. These reactions are classified as alpha, beta and gamma elimination reaction. First, alpha elimination reaction. In this reaction, the loss of atom or a group occur from the same atom of substrate molecule. For example, the base catalyst of dehydrogenation of chlorine to form the dichlorocarbene. Dichlorocarbene is reactive intermediate involved in carbamine reaction and the Riemann-Trimer reaction. Second is beta elimination reaction. In this, the loss of two atoms or a group occur from the adjacent carbon of the substitute molecule. They are called, for example, acid catalyst dehydration of alcohol and the base catalyst dehydrogenation of halide. The acid catalyst dehydration of alcohol and base catalytic dehydration of alkyl halide. Third is gamma elimination. In this reaction, the loss of atom or group occur from alpha and gamma position, means three bond away of the molecule, leading to the formation of a three-membered ring. For example, the 1,3-dibromo in the presence of Z10 dust give the cyclopropane. This is the called the Friedan reaction and exactly used for synthesis of three-membered ring. Fourth is condensation reaction. In this reaction, two or more molecules of same or different reagent combine to form a product with or without the elimination of simple molecule such as H2O, HCl, NH3, ROH, etc. For example, the two molecules of acetaldehyde condense in the presence of dilute alkyl to form the 3-hydrobutanol, and since the beta hydroxyaldehyde or ketone are commonly known as aldol, therefore this reaction is called aldol condensation reaction. Aldol, on heating with dilute mineral acid, ready to under the hydrogenation to form the alpha and beta unsaturated aldehyde and ketone. Rearrangement reaction. This reaction involves the migration of one atom or a group from one atom to another with the same molecule are called the rearrangement reaction. First is dehydration of 3-methyl-butanol and with the concentrated H2SO4 occurred that 1,2 migration of hydride ion to give the reagent product of 2-methyl-butadiene. However, when the 2-dimethyl propanol 1 is treated with H2SO4, it involves 1,2 migration of the methyl group to give rise a rearrangement product of 2-methyl-butadiene. Second, Hofmann bromide reaction involved the conversion of first amide to the one amine on treatment with Br2 in the presence of KOH. In this rearrangement, the reaction of R migration from carbon to nitrogen to first give the alkyl isocyanide, which upon hydrolysis give one amine with one carbon atom lesser than the original amide. Six is isomerization reaction which involve interconversion of the isomer in another, keeping the molecular formula as well as the carbon scatter of the reaction, and the product in fact are called migration isomerization reaction. For example, interconversion of trans-but2 into cis-but2 and vice versa may be regarded as geometrical isomerism reaction. First, 1 bromo isop 2, the 2 bromo in the presence of anhydrous AlCl3 at the 575 Kelvin. 7th type is pericyclic reaction. In this is the large number of there are the large number of organic reaction which do not involve the ions. For or free radical intermediate indicate that these reactions occur in a single step. Vice versa, a cyclic transformation state. In this reaction, the bond making or bond breaking occurs simultaneously, and the reaction do not require any catalyst, any intermediate, either by heat or light. All these reactions are called pre-cyclic reaction. For example, electrolysis or cycloaddition reaction. First is electrolysis. Involve conversion of alkyl conjugated diamine to the cyclic alkene and vice versa. Cycloaddition reaction. This addition of diamine to the diphenyl for a six-membered ring is called Diels-Alder reaction. Energy consumption. Ultimate, Ultimately, certain of the flexibility of the chemical reaction is given by the Gibbs free energy change, which is related to enthalpy change and enthalpy change by the reaction. It should be noted that the reaction proceeds in the forward direction only when the G is negative and a positive G on the another has suggests that has tendency to proceed in backward direction. Further, the enthalpy S is measured by the degree of redometer of the system. Therefore, the system is most stable when the maximum enthalpy one of the another reaction is involved and there is loss of randomness which should not be favorable, and it indicates has been found that the reaction involve a decrease in number of molecule species in going from reagent to the product on proceed only by the delta H is negative, and also the enthalpy is the large enough to make the delta G negative. Conversely, when the number of molecule species increases going from reagent to product, there is increase in enthalpy of system, and the T delta S term become larger enough to make the reaction more in forward direction even when it is not exothermic reaction. When the substance are taken in the standard state, the above when the subscript 0 is used to denote the standard state and the delta G is difference in the standard free radical energy of the product and the reagent. However, in the case of equilibrium, the equilibrium constant K is related to the delta G by the flowing reaction. It may be noted that the K denotes the extent of chemical reaction at a high value of K indicate that the reaction proceed significantly in forward direction. Collision theory. A chemical reaction is believed to be take place through the collision between the reagent molecule. The number of collisions that take place per second per unit volume of the reaction is called collision frequency. The ordinary temperature and the value of collision frequency is so high in the gaseous reaction that is all the collisions were effective and result in formation of product. The reaction should be complete within the fraction of second. However, in actually practice there is no so, because most of the chemical reaction are slow and many of them do not take place even at room temperature. This may be explained as a flowing factor. First is energy factor. For a collision to be effective, the colliding molecules must have a certain minimum amount of energy called threshold energy. Since at ordinary temperature and pressure, most of the reagent molecules do not have equal energy to threshold energy in the ground state. They have to be supplied some extra energy so that their collision may be become effective, and this minimum amount of extra energy which must be supplied to the reagent molecule in the ground state to their energy become equal to the threshold is called activation energy. Activation energy is equal to threshold minus energy of the reagent in the ground state. Evidence lesser the activation energy, faster is the reaction, or greater is the activation energy, slower is the reaction. Second, origination factor or the prohibitable factor. In some cases, it must be that even in a large number of colliding molecules have more energy than the threshold energy, still the reaction is slow, and this is due to the reason that at the time of collision, the reaction molecule do not have the proper orientation for the reaction to occur. This is called orientation factor or probability factor. Thus, the form of the above discussion it follow the first. This is called the orientation factor or probability factor. Thus, the from the above discussion it is followed that the rate is equal to collision into energy factor into probability factor. The rate is equal to PZE minus E act by the RT, where the Z is the collision frequency, P is the probability factor, E is the energy of activation, is the fraction of collision in the greater than the E act. Transfusion state theory. Transfusion state theory has been more useful in understand the mechanism of organic reaction. According to this theory, the collision between the reagent molecule lead to the formation of higher energy species called activation complex or the transitional state. These species lie at the top or at the top of the energy barrier separation the reagent and the product activation complex substitute decompose to give the product. In another word, the reagent on their way to the product way through a transition state. This sequence of events are shown in the energy profile diagram for a one step of reaction in the figure 2.1. The reaction on the rate of reaction depend on the rate at which the reagent is converted into the transition state, and rather on the another frequency has been postulated in a collision theory. Since the transition state is the equilibrium with the reagent and hence its concentration is determined by the equilibrium constant K plus, which is relative to the free energy of the activation by the reaction, where H plus is enthalpy of activation, S plus is the enthalpy of activation, entropy of activation. The activation complex of TsABC is not a true molecule since it contains a particular bond and the bond of the system is maximum. Its life is extremely short and hence cannot be isolated. It finally decomposes to give the product ABC. The free energy of the activation of the energy beside the other factor depend on the strength of the BC and AB bond. Stronger the BC bond, higher is the energy of activation, and conversely, stronger the AB bond, lower is the activation energy. Further, since the free radical energy of activation represent the energy barriers, if affect the rate of reaction higher the energy barrier, slower is the reaction, and conversely, lower the energy barrier, faster is the reaction. In this contrast, delta Z is thermodynamical quantity. It is must give the difference in standard free energy of the reagent and the product, hence does not affect the rate of reaction. We have discussed about the energy profile diagram from one step of the reaction, but many organic reactions occur at two steps. In such a reaction, the initial formation transition state first decompose into the relative less energy but more stable species than the activation complex. This chemical species, which is lesser energy but more stable than the activation complex, is called reactive intermediate. The reactive intermediate finally get converted into the product, and the another active complex is transition state. And Thus, a two-step reaction occur in two transitional states, and if the free radical of the activation of the first transition state is higher than the second, then the intermediate get converted into the product and the intermediate cannot be isolated. In such cases, the first step is rate depending step of the reaction. If, however, the free radical of activation of the second transition state is higher than that of the first, then the intermediate is quite stable and hence it can be isolated. In such cases, the second step is rate determining step of the reaction. In the above discussion, a reaction may be followed by the two steps. First, substrate plus reaction into translation state give two product, and second part is substrate plus reagent into translation state. First, intermediate, then transition state. Second, give rise to product. A detailed step-by-step description of the chemical reactions show as the flowing reagent or are converted into product as is called the mechanism of the reaction. If the reaction is involved simultaneously make and breaking of the bond without formation any intermediate is it is said to be converted reaction, and such reaction occur through a single transition state. In another word, if a reaction occurs in two or more steps with the formation of reactive or the isolated intermediate is said to be a stepwise or non-constant reaction. The number of transition states performed during a stepwise reaction is equal to the number of steps by which the reaction occurs. Thus, the two-step reaction has been translated, of which one of having the higher energy of activation considered to be rate determining of step of the reaction. Difference between transition state and intermediate and the Helmholtz postulate. Intermediate are normally called the molecule or ion posed to define the geometry and can be isolated in many cases. Even when they do not unstable to isolate, their property cannot be studied spectroscopically. Alternative, they can be trapped by the substance which are known as reactive rapid, and with them the transition state, on the other hand, is normally covalent bond or ion, since it has a particular bond, and the property of transition state can be studied in terms of Helmont postulate. It may which state that for any single reaction the step of the geometry of the transition state for that reaction resemble the side to which it closer in the free energy of activation. Thus the transition state can be described as a reagent like and product like closer in the free energy of activation. The transition state may be described as a reaction like, product like, or intermediate like according as its energy closer to the reagent, product, or intermediate. For example, a strong exothermic reaction, the geometry of TS resembles that the reaction executing bond are almost impact and new bonds are very little formed, and conversely for the stronger endothermic reaction the geometry of the TS resembles that of the product. This generalization also holds good when the reaction produced through the intermediate, and for example it is well known fact that the branching of at the alpha carbon increase the rate of SN1 reaction. Generally it is explained in terms of stability of the carbocation intermediate, but the rate enhanced does not depend upon the stability of carbocation, rather it depends upon the escape with the which the transition state lead to the formation of carbocation is reached. It depends upon the delta Z. In another word, the term Helmont postulate may be assumed that the transition state of carbocation be like any other factor which stabilize the carbocation also stabilize the transition transition state. As a result, such transition state is reached more readily by the lowering the magnitude of delta Z. Catalyst. Catalyst may be defined as a substance that change usually increase the rate of the reaction without itself being consumed in the reaction. In it first combined with one of the reagents formed by the intermediate compound, which then decompose or combine with the other reagent to produce or the product, and the catalyst is regenerated. It believed that the catalyst increased the rate of reaction by providing an alternative path from the reagent to product with a lower energy transition state. In another word, a catalyst always combined with the reagent in such a way that the energy of activation or transition state of a catalyst reaction is always lower than that of the transition state of for the corresponding uncatalyzed reaction. For example, uh, consider the catalytic effect of iodine on the hydrolyze of methyl ion of by the OH ion. This hydrolyze of CH3Cl by the OH occur one step through a transition state, and the rate depend upon the nature of delta Z. Addition of I negative to the reaction mixture produce a alternative path to involve the two-step mechanism in such a way that CH3I is intermediate. Since the iodine is a good nucleophile as well as good leaving group, there is a free energy of the activation energy for the both transition state is lower than the corresponding uncatalyzed one-step reaction. It may be noted that only the rate of reaction increase, but the delta Z of the reaction remain unchanged by addition of the catalyst. Computative reagent and kinetic or the thermodynamic control. There are the number of organic reaction in the compound under a given set of condition can be undergo a competing reagent to give a different product. Considered the, for example, a compound A give two product and B and C. Further, suppose the B is thermodynamical more stable than the C, formed faster than the A. It neither the reaction is reversible. C is formed in larger amount since it has formed faster. Since the product formed faster, because it lower free energy activation is called the kinematical control. And however, if the reaction is reversible, if the reaction is reversible, there is more necessary be the case. If a process is stopped well before the equilibrium is reached, the reaction may be kinematically controlled, and since more of the faster formed product C is present. However, if the reaction is allowed to reach the equilibrium, the thermodynamically more stable B product will be predominant product or may be exclusive product formed, and under this condition the initially less stable product C is retained to A axis than the more stable product B. Such a product which is formed slowly but because of the greater stability keep on accumulation in a reaction mixture till the equilibrium is reached is called thermodynamic control product. Most of the organic reactive intermediate. Most of the organic reaction will be occurred through a participation of certain chemical species which are generally short-lived or highly reactive. Therefore, these species can be isolated. The involvement can only be detected by the spectroscopic method or by trapping them with the more reactive substrate. These short-lived, highly reactive chemical species called reaction intermediate and reactive intermediate. Some important example of the reaction intermediate are carbocation, carboanion, free radical, carbene, nitrene, arene, or enzymes. First is carbocation. The chemical species carry positive charge on the carbon which has only 6 electrons in its valence shell are called carbocation. Carbocation are short-lived and highly reactive chemicals. Since the carbon atom carried the positive charge is called electron deficient, and Tux has a strong tendency to complete its octet by accepting a pair of electrons. Generalization of the carbocation. Carbocation are produced by heterolytic cleavage of the covalent bond in which the leaving group take place always both the bond electron of the covalent bond. Some of the reaction in which the carbocation are formed are summarized below. First, ionization alkyl halide in the polar solvent. Second is by the pronotation of unsaturated compounds such as alkene, carbonyl compound and nitriles. Third is pronotation of alcohol formed by dehydrogenation. Fourth is by determining the primary alphabetic amine with the nitric acid. And fifth is the action of superacid on the alkyl fluoride. Classification. Carbocation are classified as primary, secondary, tertiary according to as the carbon carrying positive charge is primary, secondary, tertiary in the nature. Methyl carbocation has only one carbon in, however, regarded as a species. Special cases. Orbital structure. In the carbocation are planar chemical spaces. The carbocation carry the positive charge is sp2 hybridization. The three sp2 hybridization orbital of the carbon have the 3 pi bond with the 3 monovalent atom or a group which lie in the plane are inclined to one another at the angle of 120, and the unhybridized 2sp orbital which is perpendicular to the plane of 3 pi bond is however empty. Stability of the carbocation can be explained on the basis of the law of electrostatic, which states that any factor which tend to despite the positive charge by distribution it over the rest of the molecule must thus stabilize the carbocation, while any factor which tends to interspy the positive charge must be destabilize the carbocation. First, stability of alkyl carbocation. The order of stability of the simple alkyl carbocation follow the order tertiary, secondary, primary. The order of the stability of the explained on the basis of flowing. First is inductive effect. We know that the alkyl group have electron donating inductive effect. Positive or called positive I effect. Because of the positive I effect, there the release of electron toward the positive charge carbonyl, therefore dispersing the positive charge. This dispersal of the charge lead to be stabilization of carbocation. Evidence greater the positive charge, this despite the charge lead to be stabilization of carbocation. Evidently greater the number of such alkyl group attached to the positive charge carbon, greater will be the dispersion of the positive charge and hence more stable will the carbocation. Thus, a tertiary carbocation with the tertiary alkyl should be more stable than the secondary with the two alkyl group. In turn, should be more stable than the primary carbocation one the alkyl group, while the methyl carbocation with no alkyl group will be, however, be lead to be stable. Hyperconjugation effect. The stability of carbocation also be explained on the basis of hyperconjugation. In general, greater the number of alpha hydrogen, greater is the number of hyperconjugative structure. Hence, more stable is the carbocation. Thus, tertiary butyl carbocation with the 9 alpha hydrogen and hence 9 the hyperconjugation structure is more stable than the isopropyl carbocation with the 6 alpha and hence the 6 hyperconjugation structure will turn to be more stable than ethyl carbocation with the 3 alpha hydrogen, hence the 3 hyperconjugative structure, while the methyl carbocation with the no alpha hydrogen has no hyperconjugative structure, lead to least stable. Thus, the order of the stability of alkyl carbocation follow the sequence. Tertiary butyl is more stable than isopropyl and then ethyl and methyl carbocation. Third is steric effect. As discussed above, the carbocation are planar chemical species which most of the compound from which they are obtained have a tetrahedral structure. Thus, it in the formation of carbocation, bond angle between the group increase from the 109 to 120. In another word, the group move apart, and this moving always of the group received some of the steric strain present on the starting compound. Evidently, greater the relief in the steric strain, more easier to the carbocation is formed, and since the extent of the steric relief is expressed to be maximum in the formation of tartaric carbocation followed by the secondary and primary carbocation, and least in the case of methyl carbocation. Therefore, the order of stability of the various carbocation sequences tertiary, secondary, primary, methyl. Second, stability of unsaturated carbocation. The stability of carbocation in which positive charged carbon is next to the double bond and the benzene ring can be best explained on the basis of resonance effect. For example, considered and the case the stability of alkyl and benzyl carbocation. The alkyl and benzyl carbocation are stabilized due to disperse of the positive charge through the resonance as shown below. Evidence: larger the number of phenyl group attached to the carbon atom bearing the positive charge, greater is the decolorization of the electron or disperse of the positive charge, and hence more stable is the carbocation. Thus, the diphenyl methyl carbocation is more stable than the benzyl carbocation due to greater number of resonating structure. Triphenyl methyl carbocation is still more stable than the diphenyl methyl carbocation due to the larger number of resonating structure. Triphenyl carbocation is so stable that the salt such as perchlorate, fluorobromate can be isolated and stored infinitely, and thus overall stability of benzyl and diphenyl and triphenyl carbocation follow the order. Similarly, the triphenyl carbocation is more stable than the diphenyl carbocation, which in the term is more stable than the phenyl carbopropyl cation. Effect of the substitute on the stability of benzyl carbocation. The presence of the electron donating group on R, OH, OR, NH2, and NR2 on the ortho and para position, the carbon atom bearing the positive charge tendency to stabilize these benzyl carbocation and release to the benzyl carbocation by disperse of positive charge due to plus R effect. Hyperconjugation effect in the case of R group of the substitute. Conversely, presence of the electron withdrawing group such as CnNO2, CHO, COR, COH, COOR, etc. at the ortho and para position tendency to destabilize the substitute benzyl carbocation related to the benzyl carbocation by interspecification of the positive charge due to the R effect of the substitute tux as follows. Second, stability of trophylamine or cycloheptateryl cation. The trophylamine cation is unusually stable This is unusually stable due to the reason that its aromatic cation contains 6 alpha electrons. Thus, the 6 alpha electrons are completely decolorized over the 7 sp2 hybridization carbon atom as shown below, just in the same manner as the 6 alpha electrons are decolorized in the benzene ring. Actually, the trophenyl ions are so stable that its reaction with the nucleophiles such as water, alcohol, etc. are very slow. In the stability of cyclopentyl cation, like the cycloheptotwinyl cation, the cyclopentadienyl cation should always be stabilized by the resonance since the carbon atom carried the positive charge is conjugated with two double bond, and actually the carbocation is higher unstable, and the reason for this instability is that it is an anti aromatic carbocation containing 4 pi electron. According to the HMO diagram, two of the electrons are paired and present at the lower energy of MO, but the remaining two electrons are unpaired and are present at the two different separate degenerating non-bonding MO. Therefore, these cations are destabilized by the resonance. Fourth, stability of alkyloxyl carbocation. Carbocation in which the carbon atom bearing the positive charge is attached to the heteroatom such as oxygen, nitrogen, halogen, and are also called stabilized by the resonance. For example, because of the resonance stability, methoxymethyl can be isolated as stable solid CH3O CH2 positive SbF minus 6. Fifth, the stability of alkyl cation. Like the alkyl cation, the cation is also stabilized by resonance. Although due to the presence of positive charge on the more electronegative oxygen, the contribution of the conicyl structure second is further less than the that of first. To the resonant hybridized better acetyl is the most as the stable as the tertiary butyl carbocation. Sixth, inability of the vinyl and phenyl carbocation. Carbocation in which positive charge is localized on the double bond carbon atoms such as vinyl and phenyl carbocation cannot be stabilized by resonance since the sp2 orbital of the carbon atom carrying the positive charge is perpendicular to the p orbital of the double bond, and as such they are very short-lived and chemical species. However, vinyl cation are more stable than the methyl carbocation but less than the even primary carbocation as discussed below. Relative stability of carbocation. The relative stability of carbocation can be easily measured through the heterolytic bond dissociation energy. Lower the value of heterolytic bond dissociation energy, greater is the stability of carbocation. The heterolytic bond dissociation energy of the alkyl or allyl halide are given in table 2.1. From the above table, it is followed that the tetrabutyl cation is more benzyl than isopropyl than alkyl and then n-phenyl ethyl benzenyl and methyl phenyl. 1 to shift in carbocation or 1 to rearrangement of the carbocation. 1 to shift is very common in the carbocation chemistry. The diverging force of rearrangement is usually formed by the for more stable carbocation since the energy difference in the solution because a tertiary a secondary between a secondary or a primary carbocation is about 11 to 15 kilojoule per mole, and each therefore the rearrangement of exothermic this reaction either involve 1 to hybridized shift or 1 to methyl shift. The new carbocation are formed and can be subsequently undergo the nucleophile substitution by the reaction with a nucleophile can be undergo the elimination by losing from the adjacent atom. Carboanion. The chemical species carrying a negative charge on the carbon are called carboanion. And this species of carbon and this species of carbon atom carrying the negative charge are have the 8 electron in valence shell and 6 of these are 3 covalent bond and 2 are lone pair. The carboanion like carbocation have a short-lived, highly reactive species. Even through the carbon atom carrying the negative charge has octet of electrons. The inability of the carbonate is believed to be presence of formal charge on them. Generalization of carbocation. Carbocation are the produced by heterolytic cleavage of the covalent bond in which a leaving group depart without the bonding electron of the covalent bond. This implies that every carbanion has one lone pair of the electron which it can donate, and therefore the carboanion may be regarded as Lewis base or nucleophile ducts. They are usually generated by the following method. First is by substitution, by the absorption of the hydrogen on the carbon atom alpha to nitro and cyclo to the carbonyl group with a strong base, for example. Second, by abstraction of the hydrogen tertiary acetyl in with a strong base. And third is addition by the addition of nucleophile to the alpha and beta unsaturated the compound. Classification of carbocation. Carbocation are classified as primary, secondary, tertiary carbocation atom carrying the negative charge, primary, secondary, tertiary in nature. Methyl carbocation contains only one carbon and is generally regarded as a special case. Orbital structure. The structure of the alkyl carbocation is usually pyramidal and just like that of amine. The carbon carrying the negative charge is sp3 hybridized, and three of the four the sp3 orbital form the 3 pi bond with the monovalent atom or group, while the fourth sp3 contain a lone pair of the electron. Since the lone pair bond pair repulsion are accepted to a then greater than the bond pair and pair repulsion, that the bond angle in the carbanion are much lesser than the regular tetrahedral angle of the 109. In the another word, carbanion do not have regular tetrahedral geometry but have a pyramidal structure in which the bond angle are in between the 97 to 100. Even the substitution carbocation has type R1, R2, R3 carbon are optically inactive. If the sp3 orbital contain the lone pair of electron is considered as a fourth substitute, then the carbanion of the type R1, R2, R3C become the parahedral shape and should be optically active and hence the resolvable. But in actually practice, such a carbanion takes more will be evolved, and to explain this let us assume that the parahedral structure of carbon is not rigid but undergo a rapid inversion of amine molecule. As a result, one anisomer get rapidly converted into the another an anisomer. The ultimately a racemic mixture is obtained which can be resolved. Carboanion can be also be a planar geometry. It has been discussed about that the shape of the simple alkyl carboanion is pyramidal. However, when the lone pair of the electron on the carbon atom carry negative charge is conjugated with multiple bonds, then the carbon anion are always planar. This is due to the reason that these carbon anion are stabilized by the resonance, and for the resonance to be occur, it is essential that the lone pair of the electron must be in a p orbital, and so that it can be overlap the p orbital of the pi bond. In Tuck's alternative planar structure, the carbon atom carry the negative charge is sp2 hybridized. Some the other example of the planar contain carbamine, the benzene carbamine, diphenyl methyl carboanion, the triphenyl methyl carboanion. All these carbene structure by the abstracting of alpha hydrogen atom from the carbonylic compound. For example, stability. Like the carbocation, stability of carbanion can be explained on the basis of inductive effect, resonance effect. Inductive effect. The stability of carbocation have the flowing methyl, primary, secondary, and tertiary. In order is the order this order is actually reserved by the carbocation discussed above, and the free radical later, and can be easily explained on the basis of inductive effect as discussed below. Due to the electron releasing inductive effect, the group and the intensity of the negative charge on the center atom increase, and this intensification of negative charge lead to be instability of carbocation. Evidently, greater the number of alkyl group attached to the carbon atom bearing the negative charge, greater will be the intensification of the negative charge. Hence, the more stability will be of the carbocation. Thus, the methyl carbocation with no alkyl group should be more stable and followed by the ethyl carbocation, while one the methyl group and the isopropyl cation with the 2-methyl group, while the tertiary butyl cation with the 3-methyl group should be at least stable. Type of hybridization. The stability of carbanion derived from the alkyne, alkene, and alkanes can be explained on the basis of type of hybridization of the carbon carrying the negative charge. For example, as per the S character of the carbon carrying the negative charge increase, the stability of the carbon anion increase, since the electron can be closer to the nucleus and hence lower the energy. C. Resonance effect. The carbon anion in which unsaturated pair of electron is present on the negative charge cation is attached to the multiple bond or the phenyl group are much more stable than the simple alkyl carbanion. This is due to the reason that these carbon anions are stabilized by the resonance. First, the stability of alkyl and benzyl carbanion. Alkyl and benzyl carbanion are stabilized by dispersal of the negative charge through the resonance as given below. Evidence: larger the number of phenyl group attached to the carbanion bearing the negative charge, greater is the decolorization of the electron and dispersal of the negative charge. Since more the stability in the carbocation, the diphenyl carbanion is more stable than the benzyl carbanion due to the greater number of resonating structure. Triphenyl methyl carbanion is more stable than of diphenyl methyl carbanion due to the larger number of resonating structure. Second, for the substitution on the stability of benzyl, the presence of electron donating groups such as ROH, NH2 at the ortho and para position of the carbon atom bearing the negative charge tendency to destabilize the substitute benzyl carbocation related to the benzene carbanion by the identification of the negative charge due to the positive effect of the substitute. Conversely, the presence of the electron withdrawing groups such as CnNO2 aldehyde or ketone or acid or ether at the ortho and para position tendency to stabilize the substitute benzyl carbocation relative to the benzyl carboanion by dispersal of these negative charge due to the R effect of the substitute tux. Third, the stability of the cyclopentadienamine. The cyclopentadienyl is unusually stabilized since it is an aromatic anion containing the 6 alpha electron. And these 6 alpha are completely delocalized at all the 5sp2 hybridized carbon containing as are shown below. Just in the same way, the 6 alpha electron of the benzene are completely decolorized as the 6sp2 hybridized carbon atom of the benzene. This dispersal of negative charge account it unusually stability. Consequently, it has a higher resonance effect as compared to the 155 of the benzene and the hence the cyclopentadienylamine is quite stable. Fourth, stability of carbanion carrying electron withdrawing group. Electron withdrawing groups such as C double bond O ether NO2 CN tend to disperse the negative charge by resonance and hence increase the stability of the carbanion. For example, the further large number of such group greater the stability. For example, free radical. The chemical species carrying an odd unpaired of electron are called free radical. Although the free radical are themselves electrical neutral, wet due to the presence of the odd electron, they are they are more weakly attracted to the magnetic field and hence are paramagnetic in nature. Like the carbocation, carboanion, free radicals are also short-lived and highly reactive chemical species because their tendency to acquire one more electron to complete the octet. Further, because of the tendency to acquire one electron, the free radical may be regarded as electrophile. Generation of free radical. Free radicals are also prepared by the homolytic fusion of covalent bond either by heating or light. For as given when the chlorine in the presence of HV give rise to the chloro-free radical ion. Classification. The free radical ion, like the carbocation, carboanion, are classified as primary, secondary, tertiary according to the carbon atom carrying the unpaired electron in the primary, secondary, and tertiary in nature. Orbital structure. The free radical are planar chemical species. These carbon atom carrying the odd electron in sp2 hybridization. These three sp2 hybridization orbital of carbon atom have 3 pi bond with the monovalent atom or a group which lie in a plane and are indicate to the other at angle of 120 unhybridized S2sp orbital which is perpendicular to the plane of these and alpha bond however containing the odd electron. Stability. Like the carbocation, the stability free radical can also be easily explained on the basis of hyperconjugation and resonance effect as discussed below. First, hyperconjugation effect. Like the carbocation, the stability of the simple alkyl free radical is followed by the sequence tertiary, secondary, primary, and methyl. This order of stability can be easily explained on the basis of hyperconjugation effect. In generally, greater the number of alpha hydrogen, greater is the number of hyperconjugative structure, hence more the stable the free radical. Tertiary, the tetrabutyl free radical with the 9 alpha hydrogen, hence 9 hyperconjugation structure is more stable than the isopropyl free radical with the 6 alpha hydrogen and 6 hyperconjugation structure which turn is in turn is more stable than the ethyl free radical with the 3 alpha hydrogen and hence 3 hyperconjugation structure, while the methyl radical with no alpha hydrogen has no hyperconjugated structure, at least stable. Thus, the stability of the alkyl free radical follow the sequence tertiary butyl isopropyl ethyl and methyl free radical. Second, resonance effect. The free radical which are stabilized by the resonance are even more stable than the simple alkyl free radical. For example, the alkyl benzyl free radical are stabilized by the resonance through the decolorization of unpaired electron and over the double bond or the benzene ring. Evidence: the larger the number of phenyl group attached to the carbon atom, the carrying the unpaired electron, greater is the decolorization of the electron and hence more stable is the free radical. And thus the diphenyl methyl free radical is more stable than the benzyl free radical due to the greater number of resonating structure. Triphenyl methyl free radical is still more stable due to the still large number of resonating structure. Radical in which odd electron is located on double bond carbon atoms such as vinyl or phenyl radical cannot be stabilized either by hyperconjugation or by the resonance, and they are usually very short-lived. And these radicals are even less stable than the methyl free radical as discussed below. Relative stability of the free radical. The relative stability of free radical can be measured through the homolytic bond dissociation energy for the RH bond. Greater the value of bond dissociation is lesser the stability of the free radical. From the above table, it followed that the order of stability is different for the free radical sequence. Carbenes, defined as a neutral divalent carbon species in which carbon anion is bonded to monovalent atom or a group of carbon covalent bond has the non-bonded orbital contain two electrons between them are called carbenes. These are also called methylenes. However, in actually practice, the parent species CH2 is called methylene and but the derivative are called the carbene. For example, methylene dichlorocarbene. Like the carbene are short-lived, highly reactive chemical species since the central atom has a 6 electron in the valence shell and a stronger tendency to complete it by gaining the two more electrons. Since the carbene is believed as a Lewis base as electrophile and typically the reaction which involve the carbene intermediate as carbamine reaction and the Riemann-Trimmer reaction. Generalization of the carbene. There are generalization of two methods by the terminal or photochemical decomposition of cyclopropane and oxime. Second, by terminal or photochemical decomposition of dialkene or ketone. Third, by the action of strong base, usually tetrabutyl oxide or chloroform. This is a reason is an example of alpha elimination since the HCl are lot from the same carbon atom. Type of carbene. Depending upon the distribution of two non-bonded electrons between the two orbitals, the carbenes are most followed by the two types: single carbene, triple carbene. When the when the two non-bonded electrons are present in a orbital, it two electrons are paired and another orbital is empty and the carbon is sent to be single split carbene. The single split carbene is single methylene is usually represented by the by the upper and down CH2. Since the single carbon is non-unpaired electron and it has no dipole moment and is diamagnetic. Since diamagnetic, it can be detected by the electron spin resonance stereoscopic. On the other hand, it can be non-bonded electron and unpaired are represented in a different orbital of equal energy in their spin parallel to the accordance with the Hund's rule, and the carbon is said to be triple carbon. The triple carbon can be triple methylene, usually represented as two upper arrow CH2. Unlikely, the split carbon is tripled carbon and can be permanent dipole moment. And further, since the triple carbon has the unpaired electron, if it is the parameter hence easily be detected by ESR spectroscopy. Orbital structure. In the single carbon, the central atom is sp2 hybridization. The sp2 hybridization orbital used for the 2 pi bond and the monovalent atom or a group, while the third sp2 hybridization contains the two non-bonded electrons, and this hybridization of the p block however empty. The single carbene is called carbent chemical species. The structure of split carbene is similar to that of the carbocation. Hence, in the both of them, carbon sp2 hybridization, one of p orbital is empty. In the triple carbene, the central carbon atom is sp hybridization of two sp orbital from the 2 pi bond with the two monovalent atom or a group, while the two unhybridized p orbital are perpendicular to each other and contain one electron each. Thus, a triple carbene is linear species and behave a diradical or biradical. Stability. A triple carbene is always more stable than the corresponding singlet carbene. This is due to the reason that a single carbene, the two non-bonded electrons are present in a same orbital and thus tend to repel each other. This inter-electron repulsion increases the energy of the singlet state related to the triple state, in which the two non-bonded electrons are present in different orbitals. This is supported by observed the triple methylene is about 35.5 kilojoule and more stable than the single methylene. Further, the carbon in which the central carbon is attached to the two atoms, each one of them has a lone pair of electrons and such somewhat more stable than the methylene due to resonance. Nitrene. Nitrene are also called nitrogen analysis of a carbene and can be defined as neutral monovalent nitrogen species in which the nitrogen has two unpaired of the electron and is bonded only by a monovalent atom or a group. Generation of nitranes. They are generated by the following method. First, by thermal or photochemical decomposition of azides or the isocyanates. Second, by the base catalyst elimination of sulfonate ion from O-hydroxyamine O sulfonates. Type of nitrines. Like the carbenes, nitrines are also of two types: single split and triplet. Singlet nitrines, the four bonded electron on the nitrogen are as a two pair, but in triplet these are present in the form of one pair and two unpaired electron. Orbital structure. In the singlet nitrine, the nitrogen atom is sp2 hybridized. One of the sp2 hybridized orbital form the pi bond with the monovalent atom or group, while the other two sp2 hybridized contain a pair of electron each. The unhybridized p orbital is, however, empty. The triplet nitrine, the nitrogen atom is sp hybridized. One sp orbital form one pi bond with the monovalent atom or a group, while the other contain a pair of electrons. The two unhybridized p orbitals are perpendicular to each other and containing one electron each. Stability and detection. Nitrogen took reactivity to isolate under the ordinary condition. Alkyl nitrogen has been isolated by the trapping in the matrices at 4K, and while the aryl nitrogen has been less reactive to be trapped at 77K. The trapping of the nitrogen is usually carried out by the reaction with the carbon monoxide to avoid isocyanate. Arynes. The aromatic compound containing a formal carbon-carbon triple bond is called arynes. The best known aryne is benzene, which is aromatic analogous of the acetylene. In another word, it may be regarded as a benzene minus 2 hydrogen and hence can be called dihydrobenzene. Structure. Triple bond of the benzene is although different from that of acetylene. In acetylene, it is made up of the sp and pi bond and two pi bond formed by the sideway overlap of p orbital. However, in the benzene, the triple bond consists of one sp2 pi bond, and while the sigma bond, the pi bond is formed by the sideway overlapping of the p orbital, while the other containing the sideway overlap of sp2 orbital as shown in figure. This is new pi bond lie among the side of the ring and hence a little interaction with the pi bond cloud lying above and below the aromatic ring, and since the sideway overlap of the sp2 hybridized orbital is not good, therefore the new pi bond very weak and hence benzene is highly reactive molecule. Generation and detection of arynes. By acting of the sonamide, the liquid ammonia or on the aryl halide, benzene has been shown to be the intermediate in the nucleophile substitution reaction of the aryl halide. For example, in the presence of strong base, aryl halide eliminated a molecule of HX from the O position to form diarrhea, and while the subsequently readily react with the available nucleophile to form the subsequent product. Mechanism is called the benzene mechanism or elimination addition mechanism. Similarly, the intermediary of the benzene is Dawes method of the industry product of the phenyl from the chlorobenzene, and strong ally has been demonstrated using the cyclochlorobenzene. Second, by the thermal decomposition of benzene diazonium to carbonate. Detection. Arynes are usually detected either through the mass stereometry or by the reaction such as dimerization or the cycloaddition reaction with the substance like furans. Reaction. Most important reaction of the arynes are nucleophile addition and cycloaddition. First, nucleophile addition reaction, in which an aniline in the presence of R and H2 give rise to benzene, and in the presence of H2 give rise to phenyl. As second, cycloaddition reaction. Anions are the alpha beta unsaturated amines. These are formed when an aldehyde or ketone containing pi alpha hydrogen atom react with secondary amine. The presence of trace amount of an acid such as p-toluene sulfonic acid. The equilibrium is shifted in the forward direction by removing the H2O as an azeotropic with the benzene, and the second amine among the commonly employed in the enzyme form are prolymed piperidine and moproline. The reaction of amines. Some important reaction of amines are given below. First, alkylation and acylation of ketone. Amines serve as useful intermediate in the alkylation and acylation of ketone. Thus, when a imine is treated with the reactive alkyl halides such as arylic, benzoic, formylic, and alpha haloether and alpha haloether, etc. Annihilation occurs at the beta carbon atom of the amine. The hydrolysis of the imine salt Tux form give the alpha alkylated ketone. For example, for the reaction is called the Stokes-amine reaction and exclusively give the monoalkylation product of the ketone. Therefore, it is advantage over the base catalyst acylation and alkylation of ketone, which is not stop at the monoalkylation stage. Usually give a mixture of product. Another advantage is that alkylation usually takes place on the less substitute side of the ketone. For example, the reason for the selectivity is that the imine is stabilized by the resonation between the p atom containing the lone pair of electron on the n atom and p orbital of the double bond. This required a copolarity of the bond on the unsaturated carbon atom and the nitrogen atom, which is possible in structure first but not in second. Similarly, the alkylation of ketone can be carried out by using the acid chloride instead of halide. Second, mixed type of reaction. Imines are react with alpha beta unsaturated ketone to first give the miscible type adductive which upon subsequently hydrolyze and give the 1,5 diketone. For examples, the assigned formal charge on the intermediate and other ionic species average electron theory. Defined for a formal charge, Lewis structure frequently contain the atom being a positive or a negative. If the molecule as a whole is electrical neutral, the sum of the positive charge must be equal to the sum of negative charge. Thus, the formal charge may be defined as positive negative charge which must be assigned to the certain atom within the molecule as to complete the describe the Lewis structure. The formal charge on any atom within a molecule and hence on the ion and the intermediate as a whole can easily calculated with the help of average electron theory. Average electron theory. According to the average electron theory, the center atom is covalent molecule is surrounded by the two type of electron, shared pair and lone pair. The shared pair are called bond electron while the lone pair are called non-bonded electron. The average number of electron on the central atom depend upon the number of bonded and non-bonded electron around it, whereas the bonded electron are divided equally between the bonded atom and non-bonded electron are assigned to with the atom on which they are received. In the another word, while calculating the number of average electron on the central atom, half the bonded electron are added to non-bonded electron. Number of average electron is equal to half into bonded electron plus number of non-bonded electron. If the number of average electron in Tux calculate is less than that of neutral atom, then the atom is assigned to be a positive formal charge equal to a magnitude of the difference between them. Conversely, if the number of the average electron on the central atom is more than that of the neutral, then the assign is negative charge in the magnitude to the difference between them. Once the formal charge on the each atom of the molecule has been calculated, the arithmetical sum of this formal charge gives the net charge on the ion as whole. Now the number of electron on the neutral atom is equal to the number of electron in the valence shell. 4 case in the of carbon and 5 case in the nitrogen and 6 case in oxygen and 7 is halogen. Therefore, the formal charge on the atom, the number of valence shell minus the number of average electron is equal to number of valence shell minus half into the number of bonded electron minus non-bonded electron. It represents covalent bond by a line and non-bonded electron by a dot. The above equation may be rewrite as formal charge on an atom is equal to number of valence electron minus the line plus dot. Let us not apply any theory to calculate the formal charge on the reactive intermediates such as carbocation, carboanion, and free radical carbons. First, methyl carbocation. In complete Lewis structure of the methyl carbocation in CH3, the formal charge on the carbon is number of valence electron minus the half of the number of bonded electron minus non-bonded electron, that is equal to 4 minus half into 6 minus 0 is equal to 4 minus 3 is equal to plus 1. Thus, the complete Lewis structure of the methyl carbocation is CH3 plus, and the methyl first second is methyl carboanion. This incomplete Lewis structure has contained the equal to CH3. The formal charge is -1 and the structure is given. The methyl free radical, the Lewis structure is of the methyl free radical is dot CH3 and the formal charge on the carbon is 0, and the complete structure of the methyl free radical is same as written above. Methylene. The Lewis structure has the methylene is CH2 and formal charge on the carbon is equal to 0, and thus the complete structure of methylene is same as written above. Nitroammonium ion. Incomplete Lewis structure of nitroammonium ion is equal to the formal charge on oxygen is 0 and on nitrogen is +1, and the complete structure of the nitroammonium ion is equal to O double bond N plus equal to O double bond lone pair. To isolate this rule for the considered molecule of dienzyme, which can be written as a resonance hybrid on the following three Lewis structures. But the structure not complete since the formal charge on the same of the atom are missing. Let us calculate the formal charge on each of the atom of all three Lewis structure. Lewis structure first. The formal charge on carbon is equal to -1, formal charge on nitrogen is +1, and formal charge on terminal nitrogen is equal to 0, and the complete Lewis structure as given below. This Lewis structure second. The formal charge on carbon is 0, formal charge on central nitrogen is +1, and terminal is -1. Lewis structure third. In this, the formal charge on carbon is -1, formal charge on center atom is 0, terminal nitrogen is +1, and the given structure below. Thus, the diazyme is a resonating hybridized of the following three structures. In each of these three structures written above, the sum of the formal charge is 0, and therefore the diazyme is wholly an electrical neutral molecule. Method to determine the reaction mechanism. The mechanism of the reaction implies the path which the reaction follow on the way of product. Since many chemical reaction produced were rapidly, it is not possible to follow the reaction path directly, and hence our knowledge about the reaction mechanism is mostly based upon the intermediate evidence. After the characterizing the product, the number of mechanism consists with all the experimental observation are proceed in the or in the most of the cases, a new experiment is carried out by elimination of these mechanism. If such elimination lead to be one mechanism, then it is said to be eliminated mechanism of the reaction. In the journal, the proceed mechanism for the reaction should be energetically favorable. Second, should amount for all the experiment observation, and third must be consistent with the mechanism of analysis reaction. A number of methods are used to determine the mechanism of reaction, and this include first product analysis, second detection and isolation of intermediate, third isotope liberation, fourth is isotope effect, fifth is kinematic studies, and sixth is geochemical studies. All these methods are believably discussed below, and it may however be noted that it is necessary to apply these old methods to determine the mechanism of a particular reaction. First, product analysis. The first step of investigation the mechanism of reaction is the identification of product and determination their relative amount. To isolate this point, let us consider the following reaction. First, hydrolysis of two isomeric alkyl chloride, while a mixture of 85% of the tetra alcohol and 50% are primary alcohol. Since the composition of the product remain to be same in either cases, therefore the hydrolysis of these two compound occur through a common intermediate. Second is ketoamine. On treating with an acid, undergo the Blackman rearrangement to give the corresponding substitute amide. The product analysis has been received that during this determination, the mechanism of the Blackman has been given. Third, crossing over the experiment. Crossing over experiment are useful in determining whether the particular reaction is one step, two step. In this experiment, the same reaction is carried out with a mixture of similar but non-identical reagent, and the product thus contained are analyzed to isolate the role of crossover experiment in determining the mechanism of the organic reaction. Let us discuss the free rearrangement of ether 6 and 7, which involve the migration of acyl or the aryl group from the oxygen atom to the benzene ring. These two ether on treating with the anhydride aluminum chloride undergo the similar condition, undergo the rearrangement at approximately the same rate to give the product of 8 and 9 respectively. If the same reaction is known carry out with the mixture of these two ether, undergo a similar condition of two possibility as arise. First, if the reaction occur constantly or in one step, the ether will always give the ketone while the ether will always give the ketone. Second, however, the reaction occur in two steps, then the migration group C6H5CO in the ether and the CH3CO group in the ether must be become the free during the course of rearrangement, and hence crossing over product must also be formed in addition to expect the product. In actually practice, when the same reaction was be carried out with the mixture of these two ether, the crossing over product were be isolated in addition to expected products, and therefore the confirming that the fresh rearrangement in is a two-step process. Second, detection and isolation of intermediate. Many organic reactions occur throughout the formation of intermediate, which may be either be stable or unstable. The stable intermediate is isolated, then the characteristic, and the unstable intermediate, on the other hand, are either detected by the stereoscopic method or isolated by trapping them with the reactivity substrate as discussed below. A isolation: if the intermediate are stable, they are usually isolated by stopping the reaction before it completely completed or by using the relative milder condition. For example, 3 intermediate and bromoamide, its amines and the isocyanide has been isolated in the Hofmann bromide rearrangement of primary amide to the primary amine on treating with Br2KOH. Thus, any process mechanism for the rearrangement must be amount of the formation of all these intermediate. Detection. Unstable intermediate are often detected by the spectroscopic method. For example, intermediary of the carbocation intermediate is SN1 and the elimination 1 has been established by the nucleus magnitude resonance and the spectroscopic. Similarly, the carbocation intermediate such as of tenth in the electrolysis substitute reaction has been characterized by their NMR and the elimination step. Free radical intermediate can be detected by the electron spin resonance spectroscopy. Third, trapping. The unstable intermediate can also be characterized by trapping. For this purpose, the reaction is carried out by in the presence of the compound which is known as reactive radically. Carbenes. First is carbenes. The form during the photochemical decomposition of the benzene. Carbene formed during the photochemical decomposition of dimethane in the trapped as a cyclobenzene and derivative which are decomposed is carried out by the presence of cyclohexane. Second, benzene is formed during the decomposition of benzene diamide to carbonate can be trapped by the antiacene to form the tripeptosine. Third is carbocation are trapped by the reaction damp with the nucleophile. For example, the carbocation formed during the addition of Ar2 to the ethylene can be trapped by a number of nucleophiles such as I negative, NO3, H2O, etc. Free radical can be trapped by the carrying the reaction in the presence of nitric oxide. With the help it can known is to reactive rapidly. For example, for free radical formed during the thermal decomposition of acyl sulfonitrile is trapped by the nitric oxide in the form of hydroxyamine derivative. Third is isotopic labeling. The mechanism for many of the reaction can be studied by using the molecule in which an atom is substituted by its isolate. For example, first hydrolysis of ether. The mechanism of hydrolysis of an ether, whether is involved the acetyl oxygen and the alkyl oxygen fusion, can be solved by the hydrolyzing the N-methyl acetate in the H2O. Since the hydrolysis wilt is unlabeled and is labeled acid hydrolyzed by the ether involved diacyl Canazole reaction. Canazole reaction involves transfer of hydrogen atom from one molecule to another. This question whether the hydrogen get transferred come from or the aldehyde can be solved by carrying out the reaction with the denaturated benzaldehyde instead of benzyl aldehyde. Since the denaturation is actually located on the carbon atom of the benzyl alcohol carrying the hydroxy group, the probability of exchange of hydrogen with the hydrogen atom of water is ruled out. Thus, there is transfer of denaturism from the carbon group of the one molecule to the another, and during this transfer, deterioration can be detected. A palisable mechanism consistent with the above observation can be visualized as follow. Further support of the above mechanism come from the observation that when the reaction of the benzaldehyde was carried out in the D2O, the recovered alcohol contained no alpha degeneration, indicating that the hydrogen comes from the other molecule of the aldehyde, not from the solvent. Third, nucleophile substitution benzene mechanism. When the cyclobenzene is treated with NaNH2 is in the liquid NH3, the alene is formed, and this mechanism of nucleophile substitute reaction involves a benzene intermediate as given in section 2.13.2. This mechanism is supported by the observation that when the chlorobenzene is in which the chlorine is attached to the labeled carbon, two type of alene are produced, one of which the NH2 group is attached to the C14 while the other in which the NH2 group is attached to C12 carbon next to the C14 carbon as given below. Isotope. While discussing the isotope labeling as a total or to investigate the reaction, we can has made the important assumption that there is no difference in the chemical behavior in different isotopes. So the chemical property of the compound are not quantitatively changed when a particular atom is of a compound is replaced by its isotope. However, in actual practice, the isotope become because of their different mass do not affect the rate of the chemical reaction. The variation in the rate of reaction when an atom is in a compound is relatively by isotope as called isotope effect, and usually it is very small. However, it replacement of an atom by its isotope is involved in the rate determining step of the reaction, and the magnitude of the isotope effect may be the quite larger and called the primary isotope effect. Since the mass of the deuterium atom is double, then the tritium atom is triple than the hydrogen atom, and therefore the magnitude of the primary isotope is affected, and it the greater when a hydrogen atom is replaced by a deuterium or tritium. It is usually expressed in terms of the rate hydro ratio or the respectively. The value of the rate of ratio is always greater than one of the which one that the compound containing hydrogen atom react faster with the that of containing deuterium and tritium. Typically value for the KH and KD and KH and KT is 7 and 16 respectively. The reason for the primary isotope effect is that the bond dissociation energy of the CD bond is more than that of the CH bond and even greater than the CT bond. Therefore, the energy of the activation for cleaving the CD bond would be greater than that of CH bond, and hence the rate of reaction involved in CD bond cleavage is very slow. And however, we noted that here that if the CD and CH bond cleavage are not involved in the rate determining step of the reaction, then the rate of the reaction will be hardly affected when the hydrogen atom is replaced by its isotope D and T. Most of the studies of isotope effect the being carried out by using the deuterium, not the tritium, because it is more easily available, and also become the tritium is a radioactive. Primary isotope effect and the reaction mechanism. The primary isotope effect is powerful tool in determining the mechanism of many reactions. For example, A. Dehalogenation of isopropyl bromide. The rate dehydrohalogenation of isopropyl bromide with the sodium ethoxide is considerable reduced when the hydrogen atom of the methyl group are replaced by the deuterium. Secondary isotope effect. Deuterium effect has been found that when there is certain that the CH bond does not break it at in the reaction, such effects are called secondary isotope effect, and their magnitude is squarely smaller as compared to the primary isotope effect, and these are further classified as alpha. According to the as the deuterium is present at the alpha, beta, and gamma position, the carbon atom at the reaction is taken place. An example of beta secondary isotope effect is the solubilize of the isopropyl bromide. The Ks and Kd ratio for this reaction will be 1.34, and probably reason for the secondary isotope effect is hyperconjugation. The larger isotope effect definitely suggests that the rate determining step of the reaction involved the cleavage of the CH bond, as the flowing reaction for the above reaction is ruled out in the mechanism of CH bond cleavage. In the first talks, we consider that the CH bond cleavage and the CBr bond cleavage will which is involved in the rate determining step of the reaction. B. Nitrification of the benzene. Nitrification of benzene is electrophilic substitution reaction. Here nitrogen ion attached to the benzene ring and form a carbocation intermediate which then lose a proton to give a nitrobenzene. In the case of hexatetrabenzene or hexatetride benzene is used in the place of benzene. The rate of the nitrogen has been found to be the same. This means that nitration of the benzene does not show any isotope effect. In another word, the rate determining step of the reaction does not involve breaking of CH bond. Conversely, attack of the NO2 plus on the benzene ring is the rate determining step, while the cleavage of the CH bond is a faster step. And this correct the mechanism for the nitration of the benzene may be formulated as follows. Fifth is kinetic evidences. The kinetic evidences alone is not sufficient to determine the mechanism of a particular reaction. However, this study gives the useful information about the rate determining step of the reaction. It will be often possible to rule out the mechanism simply on the basis of the rate law, and this is important example where the kinetic study has been usefully to in determining the mechanism of the reaction and is in the hydrolysis of alkyl halide. For example, the hydroxy methoxy bromide show the secondary order kinetic. The rate This rate suggests that both the CH3Br and OH negative ion are participate in rate determining step of the reaction, and such reaction are called SN2 reaction and occur in one step through the Stereochemical evidence. Sometimes the mechanism of reaction can be determined by the flowing the stereochemistry of the reagent and the product. For example, the mechanism of nucleophile substitution reaction has been investigated by the carrying out the reaction with the optical active compound, then the checking of the optical purity of the product. A mechanism of SN2 reaction: hydrolysis of the optical active 1-chloro-1-phenylethane with an aqueous KOH give rise to racemic emission 1-phenylethanol. Racemization of the product suggests that the racemic reaction occurred through a planar carbocation intermediate, since the attack of the nucleophile of OH ion on the carbocation can be formed both the phases with the almost equal case give the 50 ratio 50 mixture of the anestomer. From the above discussion, we consult that the SN1 reaction occurred through the carbocation intermediate. Mechanism of SN2 reaction: hydrolysis of optical active 2-bromooctane give rise to optical active 2-octanol. This is the explain if we can assume that the attack of the OH occur from the side of opposing to the bromide atom, giving the first transmission state, which then repel the Br ion to give the product. During the reaction, the inversion of configuration occur, and this is called von der inversion. For the above discussion, we consider that the SN2 reaction are non one-step reaction in which optical active reagent give the optical active product with the inverted configuration. C. Elimination reaction: dehydrogenation of cis-1,2-dichloroethane give the chloroacetylene 20 times faster than the corresponding trans isomers. This suggests that the E2 reaction occur more rapidly when the department growing are in transmission oriented that they are cis.